Hello everyone, welcome to the Prelab lecture for creating an alcohol. This will count as the Prelab for both weeks. In this Prelab, I'm mostly going to focus on the chemistry and the mechanism. Some of this is sort of old, but a good deal of it is going to be new, so I did want to take the time so you kind of understand what's going on. So firstly, for this reaction, we are looking at reacting one hexene, an alkene, with sodium borohydride to produce an alcohol. And our specific alcohol we're trying to make is this one right here, or we're hoping to make is this one right here. And so what we see, this is an addition reaction. In particular, this is a specific type of addition reaction. This is called an anti-Markovnikov addition. In terms of when we look at both of the carbons that are making our double bond here, or pi bond here, you see that the OH group has been added to the least substituted carbon. Right, and vice versa, the other type of addition we could see would be doing a Markovnikov addition, where the OH adds to the more substituted carbon. Right, so Markovnikov. Okay. Now, in order to do our anti-Markovnikov addition, our reagents are going to be sodium borohydride, right, as a first step, and then the second step is we incorporate the use of a peroxide. All right, now. This is very regio-specific to do our anti-Markovnikov, and there are two methods to get our Markovnikov addition, and the one that I want to focus on is one that you should be sort of familiar with, aspects of it anyway. So if we look firstly at doing a Markovnikov addition, we can do that utilizing an acid catalyst or a polyprotic acid. So in this reaction, we see that the alkene is going to act like a nucleophile. Right? It's going to take a hydrogen, and we're going to break that that oxygen-hydrogen bond, and that will create water. So we see, as an intermediate here, we produce a carbocation. So the hydrogen here is from our acid, and we, like I said, we do create water. And then we are going to see through a couple of steps, and I'm going to go ahead and show it deprotonated, but through a couple of steps, we would see our Markovnikov alcohol product here. Okay. For our sodium borohydride, when we utilize that, we are still seeing an addition reaction, as I said before. And the first step that we see in this process, our intermediate looks very strange. We're actually going to see kind of this weird box-like structure where you have a carbon-boron bond and now a carbon-hydrogen bond. And due to the steric bulk around the boron and also around the other side of this original molecule here, we see that the hydrogen can only, one of the hydrogens on the boron, the easiest carbon for it to reach, it's going to prefer to coordinate to our more substituted carbon, because this carbon doesn't have any steric bulk around it, so the boron can reach it a lot easier. All right, and so through some other breaking of bonds and forming of bonds, we would eventually see 1, 2, 3, 4, 5, 6. We would see that we created this boron structure where now our 6-carbon chain is attached to the boron, like so. And this would actually continue to react. The boron itself will continue to react with more of these alkenes until we got 6. There's supposed to be 6 carbons here. I ran out of room on my page. 1, 2, 3, 4, 5, 6. To where we got our 3 chains attached to the boron. Alright, so that is in essence our final product after our first step, adding the sodium borohydride. So in order to actually get our alcohol functionality onto our alkene, that's why we incorporate step 2, our peroxide. Alright, and so once we do that, that's when we would see 3 alcohol products that are anti-Markovnikov products, like so. Okay. Alright, and so actually at the end of week 1, this would have been our product at the end of week 1. So week 2 incorporates the use of peroxide to make our anti-Markovnikov alcohol. Okay, now, one of the, as we should hopefully remember from lecture, one of the big problems with our first reaction up here, alkenes doing an addition with our acid catalyst or polyprotic acid, when we form this carbocation, it can undergo rearrangements, carbocation rearrangements, in the form of methyl shifts or hydride shifts. But looking at these 2 different reactions, you don't really see the real importance here. So we would actually want to modify our starting structure a little bit to really understand why we see these things going on. So if instead, let's say I chose this alkene and I looked at using the hydronium, right? Same first step would happen. The pi bond attacks the hydrogen, and I'm going to turn my hydronium into water. So I would get a plus charge there. My hydrogen went there. Okay, now, since that is a carbocation, this is specifically a secondary carbocation. And remember, if we look to the left, if we look 1 step to the left or 1 step to the right, we would see that here that would become a primary carbocation if the plus charge moved here, and that's not more stable. However, if we look jumping to this side, that would become a tertiary carbocation, and it is more stable. So this acts as kind of a driving force for us to do our hydride shift. Get a plus charge there, and so the hydrogen, so that is the original hydrogen, and then this is our hydride shift hydrogen right here. Okay, so then we would see after our water adds and everything, we would actually get this alcohol, right? Which technically it is a Markovnikov product because it is at the more substituted carbon, but it's not one of our original alkene carbons. So you can see here how carbocation rearrangements can be real bothersome, all right, and they do give us less control. And we'll learn later on in chapter 7 and chapter 8 that if we want to get our Markovnikov product for an alkene like this, we can add the alcohol specifically to this carbon, but we'll use something other than hydronium. We'll use a mercury reagent to actually give us specificity and put that alcohol there. All right, but for right now, that's too far ahead, so I'm not going to focus on that. Now, vice versa, if I looked at this same alkene and tried to do my use my sodium borohydride and peroxide, I don't have to. What I saw from before here is I do not create a carbocation. So since I don't create a carbocation, it's okay. I will see that my intermediate here would still give me my boron at my less substituted carbon, right there, and then by addition of my peroxide, I would get that. So the great thing about sodium borohydride, I don't have rearrangements because my intermediate is not a carbocation. I get this. Well, first off, my intermediate with sodium borohydride looks like this box-like structure. All right, so I'm not going to have any type of rearrangement, and when I kick off my boron with peroxide, my alcohol just replaces, my OH just replaces the boron. All right, so that's some good looks at why we really even care. All right, now some things that I do want to point out here. In your procedure, it talks about using, let me find it real quick. In your procedure, we do see for week 1, step 10, it says, at this point in your reaction, you will have taken your alkene, so your alkene and your sodium borohydride, and you will have reacted them together. And it says here, once that reaction is over, you can put it in an ice bath, and then you will add distilled water to this reaction mixture. And the reason that's important is because it decomposes any excess sodium borohydride. Right, so you want to get rid of any sodium borohydride that did not react, because it does react in atmosphere, and it can create problems later on when you add your peroxide as well. So once you add the water to this mixture, you're in essence going to be seeing a reaction of your sodium borohydride reacting with water, and so it'll decompose it into H2 gas and this oxidized sodium boron structure. Okay, and so this H2 gas is actually, you're going to see this in the reaction, or you would see this in the reaction, because once you add the water, it talks about tiny bubbles. Those tiny bubbles that you can see after adding the water is that H2 gas. Okay, all right, so big picture here, water, it quenches the sodium borohydride, so you won't have any adverse reactions later on once you add the peroxide, and so you know that it will have all of the excess sodium borohydride will have reacted, because you will no longer see the formation of any more bubbles or H2 gas. All right, and so one other thing to kind of talk about here, you are creating your alcohol, right? You're creating this anti-Markovnikov alcohol, and you're going to need to adequately separate it. So later on, you will be doing a separation in a separatory funnel, and you're going to be having an organic and an aqueous layer. Now, with this OH group being there, right, you can have hydrogen bonding with this molecule. So this is slightly soluble in water, but it's also soluble in the organic layer. So one thing that you'll do to help increase the solubility, specifically in the organic layer, you will add to your separatory funnel when you have your two phases, right, phase 1, phase 2, you're going to add potassium carbonate, which is highly soluble in water, and it actually salts your water. And in doing that, right, you're going to salt your water. And so if you look at this structure has a very large non-polar chain to it, a 6-carbon non-polar chain. So it actually changes the solubility of this molecule to where it is less soluble in water and highly soluble in an organic layer. So when in your procedure, when it talks about adding that potassium carbonate, it's so that you can push all of this product into the organic layer. And then lastly, some things to be aware of. You're actually going to try, you would need to evaluate your compound after you isolate it using IR. And so so thinking about what's happening here, how are you going to isolate or determine if your reaction was a success via IR? Well, let's look at our reactant and let's look at our product. Right, so you notice the two big differences in functionality. You have a double bond, a carbon-carbon double bond versus an alcohol. So we know that this carbon-carbon double bond can be seen somewhere around 1700. We also know that if we look at the hydrogen stretch that comes off of this carbon-carbon double bond, that can be seen approximately around 3030. Okay. While this alcohol no longer has a double bond, so you wouldn't see these two bands anymore, but now that you have the alcohol, you would see a pretty broad band around 3,400. Okay, so that's some things to think about. So if you don't see any of these bands and nothing but this, you know that your reaction was a success and you got a lot of alcohol products, okay, with either no or very little alkene reactant left over. All right. All right, that is the end of our pre-lab. You may now start the quiz.